students. Myself, Professor Ankur. I welcome everyone for the gate sum session on analog circuits. Today, we are going to solve important sum on the topic of multistage amplifier. This is our fourth session on multistage amplifiers. So let's start with now sum session on multistage amplifiers. So we are going for the GATE 2016 EC paper. Let's have a look at the question. The question says, consider the circuitry shown in the figure. Assume VB1 equal to VEB2 equal to 0.7 volts. The value of the DC voltage VC2 in volts is. So here we are having a circuitry VCC supply of 2.5 volt connected to an NPN transistor where the collector and the base are directly connected to 2.5 volt. The emitter of the first transistor is now also connected to the emitter of the second transistor, which is a PNP transistor. And there is a 1 volt battery connected to the base via 10 kilo ohm. At the collector end, we are having 1 kilo ohm resistor connected to ground, and we are supposed to measure the value of VC2. So this is the question. Let's have a look at the solution. So the first thing that we will do is we will find the value of emitter voltage 1. So VE1 can be found out by subtracting 2.5 minus 0.7, where 2.5 is value of VCC, that is the base voltage, and 0.7 is the value of VBE. So this logic is basically VBE, which is VB minus VE. So you are finding the value of VE as VB minus VBE. So the value of VB here is 2.5 volt, since the base of the first transistor is attached to VCC directly, and the value of VBE is 0.7. So we get the value of VE1 as 1.8 volt. So whatever is basically the value of VE1, that is same directly the value of VE2. On similar lines, we will find the value of VB2 as VE1 minus VEB2, because VEB2 is VE2 minus VB2, and we have got here VE1 same as VE2. So substituting, you will get the value of VB2 as 1.1 volt. Now I can apply KVL to the input path so that I can get the value of VB2. The base voltage there is 1.1 volt and the battery supplied is 1 volt connection. So I can automatically get the value of base current as potential difference upon resistance. So I'm getting the value of IB2 as VB2 minus 1 divided by 10K. So it will be 0.1 divided by 10K. That will be the value of IB2. And simple logic, IC2 is beta times IB2. So when we talk about beta, the beta for the second transistor is given as 50. So you're multiplying it by 50, you'll get the value of IC2. Now, when I go for VC2, it will be IC2 into the value of RC. So the IC value is basically 50 into 0.1 divided by 10K into the resistance value, which is 1K. So solving this, you will get the value of VC2 as 0.5 volt. So this is how you solve and get the value of VC2, which is a terminal voltage, and the answer is 0.5 volt. Now this is from the GATE 2014 EC paper. Let's have a look at the question. The question is, a cascade connection of two-stage voltage amplifier A1 and A2 is shown in the figure. The open loop gain AV0, input resistance Rin, and output resistance RO for A1 and A2 are as follows. A1 is equal to AV0 is equal to 10. Rin is equal to 10 kilo ohm, RO is equal to 1 kilo ohm. A2 AV0 is 5, Rin is 5 kilo ohm, and RO is 200 ohm. So we are supposed to find the approximate voltage gain V out by V in. So when we talk about the values given, the amplifier is given with the internal parameters, that is input resistance and output resistance. So whenever we go for the gain calculation, the value of AV will be AV2 into AV1 into a factor RL upon RL plus RO2 and into another factor Ri2 into Ri2 plus Ro1. Now these factors are coming into picture all because when we talk about the output value Vout, the Vout basically is the value across the load. And for the second amplifier, the voltage source at the output end is going to be AV2 into the input value. So AV2 into the input value multiplied by RL upon RO2 plus RL will give me the value of Vout. And the input value is going to be Vi2. So when you talk about the value of AV2 into a factor, on similar lines, we will have AV1 into the factor. Because when we talk about the output of the first amplifier, the output of the first amplifier will be the voltage source and then multiplied by the input resistance of the second amplifier divided by Ri2 plus Ro1. So this is all coming into picture because of the internal connections. We have already discussed the logic of two-stage amplifiers connected back to back in the theory session where we have clearly discussed the current and the voltage relations. So this is basically direct use of the voltage relation what we have derived at that time. So now on substituting, we will get the value as 34.722. So this will be the total voltage gain of the circuitry. So this question is from the GATE 2015 ECE paper. Let's have a look at the question. The question says, in the AC equivalent circuitry shown, the two BJTs are biased in active region and have identical parameters with beta much greater than 1. The open circuit small signal voltage gain is approximately dash. So now if you observe the figure carefully, there are two transistors. The lower transistor is a NPN transistor. The top transistor is a PNP transistor. And if you observe, for the lower transistor, the collector is working like the Vout point, the base is working like the Vin point, the emitter is grounded. And for the top PNP transistor, the collector and the base are actually shorted. So we are having the Vout point at the collector end and the emitter of the PNP transistor is connected to ground. So if your observation is very sharp, the value of Vin with respect to ground will be as good as the value of VBE for the NPN transistor. And the value of Vout for Vout measured with respect to ground will be as good as measurement of the base voltage with respect to ground for the second transistor. So that's the reason when you find VO, the value of VO will be VB2 and the value of VI will be VB1. But since the lower transistor is a NPN transistor, so the value of VI or Vin, which is going to be equal to VB, it is going to be equal to plus 0.7. And when you talk about VO, which is actually VB2, which is the voltage value of the second transistor, which is a PNP transistor, so that value will be equal to minus 0.7 volt. So when you take a ratio of VO by VI, the value of the voltage gain will come out to be -1. Hence the correct answer for the open circuit small signal voltage gain is approximately -1. Thank you.